Hello Year 11. Today we are going to be looking at inverse matrices. So in the last matrices lesson, inverse matrices. In the last matrices lesson, you finished off by looking at determinants of a matrix. So if we have a matrix A, which is A, B, C, D, then the determinant of that matrix is a number, and it is AD minus BC. The determinant of a matrix helps us find the inverse of a matrix. Now, before I talk about inverse matrices, I want to talk about inverse in some other scenarios. In addition, there is a number which is the identity under addition, and it is 0. So in addition, 0 is the identity. What that means is, if you add 0 to anything, it preserves the value of the original thing. So A plus 0 is still just A. 3 plus 0 is still just 3. And so in addition, 0 is the identity. In multiplication, any guesses what the identity is? The identity is 1. Oh, you can't see that bit. I'll put it down here. The identity is 1. Why? Because 1 preserves value under multiplication. A times 1 is A. A has remained the same value. 4 times 1 is 4. So an identity under any operation is whatever preserves the value of the number or object it's applied to. In addition, 0 is the identity. In multiplication, the identity is 1. You've also seen the identity matrix. The 2 by 2 identity matrix is this, and whatever matrix I multiply it by, I don't even need to perform the addition to know that it will become the same matrix. Its value is preserved. And that works even though matrix multiplication isn't commutative. It does matter what order we do it in. It doesn't matter when we're multiplying by the identity matrix. So this will be the same as well. So the identity matrix is the same as the number 1 under multiplication and the number 0 under addition. But today we're looking at inverses. So what are inverses? Well, the inverse of something is whatever takes it back to the identity. So under addition, if I have 3 and I want to add something to it to take it back to the identity, I would need to add -3. So -3 is the inverse of 3 under addition. What about under multiplication? Let's use the same number. Let's use 3. So I need 3 times something, which takes it back to the identity, which is 1. So I need to multiply it by 1/3. Therefore, 1/3 is the inverse of 3 under multiplication. So if we're talking about inverse matrices then, if we have a matrix A and a matrix B, if when we multiply them together we get the identity or an identity matrix, then these are the inverse of each other because they've taken each other back to the identity matrix. Now we have special notation for the inverse of a matrix. So the inverse which we denote A to the -1. So similarly to how we do sine inverse and cos inverse, this is A inverse. So the inverse, A inverse, of the matrix A, you can't see that top bit, keep forgetting. Will give us the result, or we can say satisfies, A times A inverse is the same as A inverse times A, even though they're usually not the same, and that will give us the identity matrix. It is only square matrices that will have an inverse. So a 3 by 2 matrix will not have an inverse. It is only a square matrix that has an inverse. To find the inverse of a matrix, we have to use the determinant. And you only know how to find the determinant of a 2 by 2 matrix. So you will only need to find the inverse of a 2 by 2 matrix. So the inverse of the 2 by 2 matrix A equal to A, B, C, D is A inverse equals 1 over AD. Oh, I'm going to write this further up so that I can show you something else. A inverse equals 1 over AD minus BC multiplied by D and A swap places and B and C both become negative. Now this AD minus BC is the determinant of the matrix, so that is actually 1 over determinant of A, D, negative B, negative C, A. So that is how we find the inverse of a 2 by 2 matrix, and you will only need to find the inverse of 2 by 2 matrices. Now it's important to note that we're dividing here by AD, BC. So this only works if AD minus BC, I keep saying AD, BC, don't I? I mean AD minus BC. This only works if this is not equal to 0, because otherwise we would be dividing by 0. So matrix A only has an inverse if its determinant is non-zero, i.e. if AD minus BC does not equal 0. If its determinant is 0, then the matrix A is said to be singular. It does not have an inverse. Okay, so make sure you've got those notes copied down. Go back and pause if you need to, and I'm going to do an example now. So example, find the inverse of the matrix A equal to 4, 8, 2, 6. First, we need to find the determinant of A, and that is 4 times 6, A times D, minus 8 times 2, B times C, and that gives us 8. So then, A inverse is 1 over the determinant, so 1 over 8, multiplied by, I'll just show you this again. So it's 1 over the determinant, and then A and D swap places, and B and C stay where they are but become negative. So A and D swap places, B and C become negative. Now, you generally do not want a fraction in each of the entries of a matrix. You want to factorize it to some extent. However, we also want to simplify it as far as possible. All of these have a factor of 2. So I can half these, which will mean the fraction outside will now be a quarter, and this will be 3, negative 4, negative 1, 2. And that's it. So this matrix here is the inverse of A. If I multiplied these two together, including the quarter, I would get the identity matrix. And I'm just going to show you that that works. So A times A inverse is, now the quarter can come to the front, 4, 8, 2, 6, 3, negative 4, negative 1, 2. Four times 3 is 12, 8 times negative 1 is negative 8, so we've got 4. 4 times negative 4 is negative 16, 8 times 2, positive 16. 2 times 3, 6, minus 6. Negative 8 plus 12. And I've ended up with the identity matrix. So it works. This A inverse gives me the identity matrix. Last example, and this is question 1A from the worksheet. Show that matrix A equal to 4, 8, 2, 4 is singular. Now remember what we said earlier in the video, a matrix is singular if it has no inverse. It will only have no inverse if the determinant is 0, because to find the inverse we'd then be doing 1 over 0, which, as you know, breaks maths. So to show that a matrix is singular, we have to show it has no inverse. Because the determinant is 0, A is singular. That should be everything you need to have a go at the questions that I've put up. If you get stuck or you have no idea how to do a question, just let me know on Show My Homework and we can go through it in our next live lesson.